times between 15 and 16 minutes. And the value of interest is the 95% value, which is 15 minutes, 57 seconds. So, therefore, the 95% time evacuation or mustering time for this ship is about 16 minutes. We then add the 10-minute safety factor, which gives about 25 minutes, and which is well within the time range for this type of vessel, which is 40 minutes. Heaviest congestion is on deck 7, and is well within the limits stipulated by the regulations. Zone 1 is the last zone to muster in each of the 50 simulations. Let's look quickly at the effect of heel and trim. At 10 degrees heel, there isn't much impact on the evacuation time. However, at 20 degrees heel, there is a 40-second increase in the evacuation time, which could be considered significant. The effects of increasing heel can also be demonstrated by the arrival of people in Zone 1. As you can see here, there is about 10% reduction of the population of this zone with a 20 degree of heel after 10 minutes. Right. Now I'm going to look at the incorporation of smoke and fire on the evacuation. For the fire simulation part, we use a CFD package called SmartFire to simulate the spread of fire. SmartFire is also developed by the University of Greenwich within their Fire Safety Engineering Group and has many advanced features which are listed here. IMI guidelines provide a safety margin to take account of issues excluded from the analysis, such as heel or fire. However, it is now possible to include some of these issues in the simulation. Again, a night case where all passengers are in the cabin will be demonstrated. The fire starts on deck 6, and we are only going to consider heat and smoke in this scenario. And I must point out that we are ignoring the effect of sprinklers and firefighting in this example. Also, we will not be changing any of the response times of the population. Here we have the simulation in SmartFire of the heat contours. So this is SmartFire running, and it's showing the heat building up in the fire compartment and spreading out along the corridors. Here we have the simulation of smoke in Exodus. As you can see, it builds up. It builds up around the compartment the fire starts in and spreads out along the corridor. Now for the results. The 95% time is increased to about 32.5 minutes. This does not include the IMO 10-minute safety factor, since it could be argued that it's not appropriate to add the entire safety factor, since we are now including some of the features that the safety factor is meant to account for. Therefore, you could argue that this vessel has passed the IMO specified 40 minutes, as stated. However, one thing that should be pointed out, there's a significant difference between the fire and non-fire scenario, is the likelihood of casualties. Therefore, as a summary of the results obtained from this fire scenario, we have a 32.5 minute evacuation time, and I'll put double question marks for the IMO safety factor, because, as stated earlier, is it appropriate to add the complete 10 minutes? So, again, on principle, this vessel passes the requirements. However, there is 26 fatalities. Fatalities all occur between 7 and 19 minutes. They're all on deck 6. Average travel distance of 5 meters of the fatalities, and the reason for death is their proximity to the fire and their long response time. Right, here we have the representation of the passengers still in their cabins and some of the smoke spread. Here we have the contours for the smoke within Exodus. Notice the density is in the cabin and in the corridors. Here we have the start locations of the fatalities. They all start in their cabins. And here we have the death locations of the fatalities. Notice that they're all in the corridors where the heat was quite severe. Here we have the paths of the fatalities. As you can see, they travelled approximately about 5 meters. Here we have the mustering. Here we have the time to muster. If you look, the arrival times at the muster station is longer, and the reason for this is people are affected by the smoke and are forced to crawl in the evacuation. Fatalities all occur between about 450 and 900 seconds. So, as a summary, it should be noted that the majority of people are not exposed to severe conditions. However, several people are likely to have, suffer serious injuries. For instance, we have 2 people here with high doses of fractional effective heat dose, and there's a large number of people who are exposed to, if we go back to this slide, previous. If I go back, 25% of the people on deck 6 receive doses of radiation greater than 10% of fatal dose, which is very important to establish what effects will happen after the evacuation. If we had if we had toxic gases, if we had considered toxic gases, death tolls and injury levels could have been expected to be far worse. Equally, we haven't considered the activities of the firefighting system, which would have countered some of the impact of the fire. Here we have, I seem to have lost, anyway, I had a slide there which it compared to 2 simulations. So if we had compared the 2 simulations, we would notice that obviously that muster stations, people generally took longer to clear. The decks below the muster deck generally take longer to clear. Evacuation times on the lower decks in the fire cases are affected by smoke and are forced to crawl. Also, I had a comparison of the clearance time between the decks, between the non-fire case and the fire case. And this is useful in identifying areas of the ships which would have required further attention. One thing that should be noted is the difference between the actual fire and non-fire case was actually the simulation time took more than 600, was actually longer by over 600 seconds. So we had an increase of about 15 minutes. So now for the conclusions. Ship safety procedure models will bring important issues of safety procedures to the design of ship design, to the floor of ship design. They can be used to investigate realistic scenarios. Onboard versions of the software will allow ship operators to train staff and help them with firefighting and passenger evacuation. Use of sophisticated evacuation tools will enable fewer arbitrary assumptions to be imposed and allow conditions to be modelled rather than assumed. Okay, there's a slide there which was meant to talk about the demos going on later on today. Okay, thank you.
Thank you for the presentation. Questions? Okay.
Hi, Hubert Klüpfel from Trefco, Duisburg, Germany.
Yeah.
I'd like to ask you a question about the connection or the influence of the heel. What's the quantitative influence? Do you represent it by a speed reduction factor or something like that?
What do you mean the impact?
Well, you said you had this heel case, right? And what's the influence of the heel in the model?
Yeah, we got a speed factor. We obtained data from the Sheba test rig, and we looked at the impact of passengers, people's travelling speeds at increasing heel and trim. Yeah, we got a function depending on the angle and the speed.
Ed Galley, just to respond to that, as Pete said, at the moment what we've incorporated into Maritime Exodus are the reduction factors in travel speeds that we've measured on the flat and up and down stairs. And in fact we've used the data from Sheba and also from the T&O data sets. You can choose whichever data set you'd like to use. They are different.